classifications really winds up being, and at the top level, one of two things. Motion or process. Now, from a production standpoint, most of what you're going to see is process. Where you get motion is specific parts of a process, like a robotic arm moving. That's a motion. Things we have to control, carts moving or belts. That specific chunk is a motion. Overall manufacturing is going to be a process. On motion control, the physical motion of an object, and it really comes down to a couple examples: robots, parts insertion machines. Think of automatic screwdrivers going forth. Although most screwdrivers usually are not that automatic. You usually get turn on, turn off, and you have to do it by hand. But there are some automatic robotic. This fit more into robotic arms. The things we worry about are position, velocity, or speed, and acceleration. From a mathematical standpoint, it's a second order equation, polynomial. In differential equations, we would call this, x, derivative of x, the derivative of the derivative of x. In other words, the rate of change of x, the rate of change of the velocity from a mathematical standpoint. As technicians, you don't have to worry about the math behind it. The engineers will understand this, hopefully. When you do calibration, what you'll see is you're calibrating usually three factors. And they usually are the coefficients of those terms. So that you normally have, you don't need to know this part of it there, but to give you a feel for what you're calibrating, a little bit of calculus. That's strictly positioned. This is velocity. And this is acceleration. And we'll put this in terms of a little bit more understandable. The rate of change of x with respect to time. And this is the rate of change with respect to time of the rate of change with respect to time. X is the position. The belt's so many feet over, start, beginning, somewhere in between. That's the position. How fast does that belt move in general? And the acceleration is, you start from zero, the ramp up, and when you start to brake, the ramp down. If you have any changes like a box drops in the belt, that will slow the belt down temporarily and pick back up. If it's something like moving a robotic arm, it's the same sort of a thing. It's for every axis, every single motor, there's a start from zero, the ramp up the movement, the ramp down the movement. Now, anytime you have to calibrate a device, you wind up with this. Now, in calibration, as a technician level, you actually will be given a procedure that say, follow these, take these data points. In the controller, usually there is a program that runs through those data points, comes up with a calculation of, okay, now I know how to program this. So what you wind up doing as a technician is you wind up taking the data that generates the K1, K2, K3, the weighting of this. That's what you're actually doing when you calibrate a system with. Now, calibrate things such as robot arms moving, motors ramping up and down for driving belts. It could be something like flow, for instance. Flow rate actually winds up following this as well. It's a motion. The motion is, we start off at 0, we want to flow rate a certain thing, ramp up the flow rate, and ramp down the flow rate. Why do we want to ramp up and ramp down flow rate? Think of such things as water hammer, air hammer effects. You know, in plumbing, the simple fix is, at the very long end of a water run, what do? Is put a little stub with air in it. What's the purpose of that air stub? You may have this in your house or not. Depends if you have a real long run, you know, like the street entrance. For water, long pipe run, at the tail end, it may end in some sort of a valve. Sometimes you see a little T put here. That's stub, capped off. That stub will have air in it. You see this a lot around washing machines, laundry rooms. You turn on a large flow of water, okay? What happens in the pipe is before that flow of water, you start to pressurize. The water has to go someplace. Why air? See how many people remember this hydraulics pneumatics class? Well, you know, liquid is constant volume. Air is constant pressure. So what can air do?
Compress.
It can condense. So you got too much volume of water coming through here. Where does it go? It goes in a little stub. The air here compresses, it does generate more force, but at least the water has someplace to go. That's part of the deceleration part, is all of a sudden you may turn on water too fast for this piping to handle. And that's what this air hammer does. Is it literally sucks up temporarily, and it's very quick, usually about a second or so, absorbs the water, and then this helps discharge it back in through here with a washing machine. You see this around washing machines a lot, but in real long homes, you'll see this for that reason. The washing machines are a big one. Showers a little bit, but why washing machines? The biggest flow of water. Also, the other thing you see on washing machines is the discharge from a washing machine. You know, why can't you take that discharge of a washing machine directly into your sewer pipe? Because that water is so immediate and so full of volume, it's got to go someplace. The pipe's not big enough. So it's got to back up someplace. That's why you have a certain limitation as far, you know, how do you put water in. Many people in basements, you'll see this big laundry tub, sink, so to speak, is what it looks like. And you pour and the washing machine dumps water into that, and that drains to the sewer pipe. What does that do? It absorbs the water, creates a big volume space of water to delay the water going down the sewer, so the sewer line can handle it. Those are the type of things that go into play there too. When things are happening too fast for downstream, you need to have some way of absorbing that acceleration. So acceleration isn't infinite. You have to slow it down somehow. And how to come up with those numbers, or just how to come up with something that works, is the first beginning of calibrating a system. Now, in the case of the plumbing thing, obviously plumbers do this, so it's not what you call a great engineered thing. And there's standards for it. But as you sit there in a process control system to line up robots and that sort of thing, a lot of what you look at is how fast the arm moves, how fast it goes up in speed, how much it slows down. On motors, when you do in motor drives class, you have to worry about ramp up time and ramp down time. Why? Because what the motor's driving, that load, may not want to ramp up that fast. There's certain linkages, and that has to be programmed in. Because motors basically will respond like this. They get pretty fast, and that may be fine for the motor, but it may not be fine for the load that's driving, like the escalator belt. Now, can you imagine going to Nordstrom in the Augusta Mall there, and the elevator belt and the escalator just takes off immediately? Launching people and packages left and right off the thing. It actually wouldn't work like that because it's such a heavy belt. It does take some time to ramp up. Then you have service factory motors, that sort of stuff. That's a lot of, when you're going to see motion control, most of what you're going to see is going to be that effect. But notice it's restricted to acceleration. There's no third power of x, so to speak. Really can be described as position, velocity, acceleration. By that time, that pretty much covers everything in motion from a practical standpoint. Hypothetically, yeah, you go on to infinity. But from a practical standpoint, it really can't be measured that well. So we stop there, and just about everything, including sending rocket ships to the moon, get covered by that. So there's really no reason to go any further. It is that simple mathematically. Now, the things to consider, measuring, what can we measure? Usually we can measure velocity to some degree, but usually we measure position. Even if we measure motor speed, how did you measure motor speed in IMT 121 class? You got a little piece of tape on the shaft, and you had your tachometer measuring it. And you really measured, where the shaft was, the position of the shaft from an angular standpoint. When the shaft reached in alignment with the tack, you counted. When it was out of alignment, you didn't. That's position. Position of the shaft, think circularly, every time it hit this angle, you counted it, 1 plus 1. After a minute, you got a few thousand of these. Now, of course, this thing updated every few seconds, so it didn't count a full minute's worth to get revolutions per minute. It counted usually about maybe 6 seconds, multiplied the number times 10, you have it. That's normally how we do measurements on it. Shaft encoders are exactly that, they're positional. And from the position, we say how many times a second or how many times a minute do we reach that position. That's your velocity. Acceleration is more mathematical. We sit there and look at position and velocity, and over time, we take a few measurements of that, and we get a general curve that tells us what the acceleration is. Like for instance, if let me get rid of this. If we ramp up and I measure once a second, my measurements, x equals 0 inches, and x equals 1 inch. Then x equals 3 inches. Then x equals 6 inches. At this point, what's the position?
6 inches.
6 inches. What's the velocity?
6 inches per second.
A little tougher.
3 inches per second.
It's going to be inches per second. That's velocity. It's not exactly 6 inches per second, because this took what? Took 3 seconds to get to 6 inches, but that's an average velocity over the time period. Instantaneously, this is probably closer to 0, and that's probably closer to 6, to be honest. The 6 is not necessarily incorrect. We're going to get to an acceleration here. And for velocity, you normally use 2 of these. And what we notice about here is in terms of 1 second, how fast did it move?
3 inches.
3 inches. So we saw 3 inches per second. And now for an acceleration, second order equation, notice for position, we used one dot. For velocity, we used 2. So for acceleration, guess how many we're going to use? 3. I'm going to do this, so it's going to give us more of the acceleration here, and the velocity was here, but still, for acceleration, notice that the rate here was here, 2 inches per second. Here, 3 inches per second. So we wound up with 1 inch per second. In other words, every second we increased an inch at that point, and that's our acceleration factor. Now, I'm plotting this out as a calibration. 1 point gives us a position. 2 points can give us a velocity, a slope of the line. Remember y equals mx plus b? 1 point gave us b, that's your y-intercept or x-intercept. 2 points gives us that slope, m. And if that wasn't a straight line but a curve, we need a third point to get the depth of that curve. And that's where acceleration comes in. If you have a constant velocity device, that's 0. But if you don't have a constant velocity, then that does come into play. Now, it may be, in practice, you may not care that much about acceleration, and we can be a little sloppy about this. Someone ignore it. We do eventually want to get to the velocity we want, if we're turning it on or turning it off. So there's going to be some acceleration. Again, from a mathematical standpoint, I'm not concerned you generate these equations. That's something for a control system engineer. I'm not sure that half your process control engineers could follow this. Talk to a bunch of them. Some do, some don't, various degrees. But to calibrate this, almost every technician wants a calibrating process system similar to this. So in the calibration factors, what you're doing is you have a built-in acceleration velocity position. This is how it's measured. It's literally every 3 points generates an acceleration, every 2 points generates a velocity, every 1 point generates a position. And the computer just keeps track of these numbers as they go along. Like for instance, if we were to look at, in red, at this point, I would probably use this for position. That would have been 3 inches. I would look at this for velocity, and that gives me 2 inches per second. And I would look at this for acceleration, which would still give me an increase of from 0 to 2 or 1 inch per second squared. So from here I can see in the red versus the blue, I guess, I went from 3 inches to 6 inches of position. Velocity went from 2 inches a second to 3 inches a second, but my acceleration was the same. Following that, instead of 3 here difference, I would see a 4 difference. The next step would have been probably 10 inches equals x. And at this point, we would have seen this to go to 10 inches. The instant velocity here, 4 inches per second, and the acceleration would still be 1 inch per second squared. Steady state ramp up. What that would look like positionally, as you can see, 0 to 1 to 3 to 6 to 10. If you were to plot that with respect to time, it gets a curve that starts to look like this. And you can plot that curve with these measurements. And it's simply, in this case, 1, 2, 3, 4, 5 measurements. That's easy to take. I mean, you should do with a shaft encoder, whether it's position on a belt, something. Considering it's in inches of position, I'm guessing it's a linear drive and the ramp of it, and the ramp is a steady ramp up in this case. That's not always the case, but if we did have that, this is kind of an idea of the plot. And from a technician standpoint, you would take measurements. The program that you're taking measurements on, usually it's the PID controller or the controller for the system, would be able to take this information in and construct this. And then from that point, it's an optimization. And usually they give you, and you'll get into this in the lab actually, Rungakudo will be what you use in the lap 1, lap 10 I think it is, overlay system. You'll also have a spreadsheet later on next month that do some spreadsheet exercises to show calibration and loops and loop response, all based on this. As I said, it's mainly just follow procedure, take measurements, input them in a controller or some sort of computer. Usually it's the controller itself that does this. And there would be a built-in program into that computer that will calculate, you know, the 3 coefficients necessary for that second order differential equation. So from a standpoint, at least the math's taken out, kind of like the NEC does, takes out the math as far as calculation of safety factors, and says, use these straight tables, use these straightforward formulas, and you're done. Same thing for process control. But it's more or less to give you an overview of when you take these measurements, what are you doing? And I find that's helpful to understand what you're doing when you do this, to get an idea of how much care you need to put into these numbers, what do they mean, as opposed to totally meaningless, why you bother doing it. There is a reason to do it, and that's what we're developing here. It's kind of like a floor. When you go to an assembly area, it's helpful for the assembly techs to understand what they're building. You know, in the case of tires or flooring, they can see tire, so they know ultimately it's going for tires to go to cars. They understand that. It gets to be more, I'm going to call it esoteric. It's a fancy word. Stuff that's not too obvious to the average user what it means. It's helpful to see it, the product and process, to say, okay, that's what I'm working on building. How many of you at work? How many of you work to some degree? How many attend work? Hey, it's a better approach for you. I know better. Isn't it helpful to know what you're working on? You know, and that's important. So that's the same thing in process control. It's important you understand that you see what process control is and what it's trying to do as you go about it, because you're going to be one of the primary people that really keeps us running. This is not an operator level thing. This is a technician level thing, but it is a technician level point to calibrate it, get it properly running and going. The engineers kind of supervise over it, but supervision usually means they're out of the way unless there is a, you know, unsurmountable problem. They're your backup. And most problems, you see, engineers are your backup. If you can't directly handle a problem, it's okay to bring an engineer over. Should be. Places I've worked, they're successful. That's normally the way it's done. That should not be a problem. Servo mechanism is a term for it as well. And printing presses, anything that has something that moves. Notice here that the motion is actually a part of the system. It's not usually the whole system unless you're throwing it over the wall, so to speak, out of frustration. Process control is the bigger picture area, and that's a matter of usually workflows, level, in this case pressure, temperature, level, flow, pH, humidity. These are typically considered to be the 6 big things in process. And I'd mentioned earlier, when you really get down to it, level and flow are pretty much encompass everything, because it's either instantaneous or it's an accumulation factor. Now in this case, flow is the ultimate and instantaneous. Most of these other ones will have some accumulation to them. I don't know why level would show a level there. I would show a tank with a level of water. It's more appropriate. But on control, when you actually have this batch and continuous, this is interesting from the standpoint that you're either making batches of things or it's a continuous flow. A very good example of continuous flow, I think, is, how many of you have been to Krispy Kremes?
Oh, yeah.
And you see the original donuts continually rolling off the belt.
Mm-hmm.
They start up early in the morning and just keep throwing more stuff in the back of it there, and then the output end of it there rolls off donuts. They continue boxing, and it goes on throughout the day. Usually sometime early evening they finally stop, and that's it. That's a continuous flow. They're constantly putting dough in the machine, they're constantly rolling donuts, they're constantly glazing them, baking them, and they're constantly pulling them off and boxing them. They don't stop. That's not really done in a batch. It's like you think of a batch of cookies. This is just a continual roll of donuts for about 8 hours a day, roughly. That's a continuous process. A batch process would be like if I have my oven at home and I open up my can of Pillsbury chocolate chip cookies, I stick them in the oven, I cook them. At the end of that, I take them out, I put them on a drying rack, and I break out the next tube of Pillsbury cookies, and I do it again. That's a batch process. Every can is a batch. And I maybe make 3 or 4 batches for Christmas. For whatever reasons, package them up later and give them to neighbors or whatever. That's a batch process. At home, why is it a batch process? Because typically I don't have an oven big enough to handle it in one shot, so it's not one batch, it's little batches. But it's not a continuous process. In other words, I have an oven tray rolling through with back-filled cookies, one right after the other. I don't have that set up. I have a setup of one oven. Actually, it's 2 ovens in my case. And racks. Batch processing, sequence of timed operations on a product. It's a sequence of operations, but you make so many of a product, stop, make another bunch of product, stop. Now, in cases like Bridgestone, the off-road follows this pretty well. You do have a certain amount of tires in order, they're made, tested, that stops, next different set of tires come into play. We have more smaller items. It tends not to be so batchy. I said, really, the best example I can think of is Krispy Kreme donuts. Individual donuts, almost nothing, but it's just a continuous stream. It's really backfilled. And what you see in the process, in those type of operations, like for instance here, making a batch of cookies. We can see chips, milk, egg, the oven turns on. We cook them, they roll through.
Yeah, mix them up
There's
first.
a mixer, makes the dough, drops a boatload of them. You can see individual parts turn on, and it stops and cooks. And they roll up the conveyor belt. Then after this is done, then we go on to the next one. Now, if I'd say foods, the exception is original Krispy Kremes would be a good example of batch processing. Usually it's oven size that controls what it is. Arguably pizza starts to get a little less batchy if you go to say Little Caesars with Hot and Ready, because they have a standard group of them. They keep running through the oven, which they put input of oven one side to come out the other oven. They're timed. But even that's kind of a batch, kind of an in between. Controlled variables. It's actually controlled variables in everything. Raw materials fed into a machine, and stuff comes out. And without interruption is the big deal. Now, as we get to large processes, they tend to be looking like this in general. If you go to a car manufacturer, they tend to start to follow a continuous flow. Parts of it may be batched, but usually it's continuous flow in a car. Final assembly plants like in Spartanburg, Greenville are good examples of the continuous flow. Automobile parts come in, they bolt them, but they keep flowing through the factory, as opposed to stop out. Now here in generating paper, this is a good example of it. Run the wood chipper and washer, and notice that it's really a fill-in. There's no one place where you stop something, work on a chunk of it, and move it. That's kind of batch. In this case, everything's continuous. And the parts we have that are problem with the continuous is constant flow. If you have so many gallons of liquid wood chips going into a washer, for instance, you need so many gallons coming out at the same time. So here on a process, your blocking points are the parts that are a little slow for the system. That tends to block up the entire system. In batch, you don't have this. If something's a little slow, so what? But in continuous, you start to see more of the effects of, gee, this takes a little bit more time. Wire, textiles, plastic bags. Notice here these are going to be more commodity items. That's the bigger deal versus batch. Water treatment really is a good one here. Because I mean, water is a constant flow, right? Keeps going in the tower, keeps getting used out of the tower. So, in what type of control the set point is constantly changing? And that's a good question. Typically it would be motion. And the reason it's not process is a continuous thing typically. It's more of that same target. Motion, you're trying to get a robot arm, so it wants to be here right now, then there, then here. And that's where it comes from. In control, the set point typically remains unchanged, the variable remains in a constant condition. Well, if motion was it for changing, you guess process control is it for unchanging. Repeatability, in other words. Response time for motion control systems is typically something a responsive process control system. The response time for motion control has to be faster because think of a robot arm. If you overshoot your target, you overshoot it. In the process, it's possible you can come back and stop. But you know, if you're driving, and this is an example of you're driving down the road, the person next to you there is giving you directions, and they tell you too late. What happens? You drive past the turn, then you make all that bit to come back. So typically, motion control is where you want your speed, your fastest speed. Sequence of timed events executed on a product.
Continuous.
The sequence is a batch. It actually was in the viewpoint here. Batching is we take a sequence, we time it, done, boom. Get the next one here. I understand when you're thinking of continuous. Production of plastic garbage bags example of that's a continuous process. Now to get back to the time sequence, are continuous motions timed? And the design of them is yes. We don't really think of it as a time sequence. It's just the whole process is moving. A sequence of individually timed events typically is more of a batch. Like you spend so much time in the oven, so much time in the food prep, so much time in the packaging in a box. And in a continuous motion, they would all be the same times, because otherwise you have a bottleneck. In a batch, you don't necessarily have a bottleneck, so you may have to allow more time for something, in which case it is a bottleneck, but it's put in batches. Batches will tend to have bottlenecks. Continuous processes typically will not have those in there. Because bottlenecks of continuous is deadly. It stops the whole production line versus a part of it. This is meant to be an overview of thinking of, you see a batch, you see continuous. Next, I'm going to start into the types of control, and this is more of how do we manipulate, on a manipulated variable, how do we handle it? And there's on-off control and there's proportional control. And rather than get started into that, I will start off with this bit. Difference between on-off and proportional. Proportional is, I have a valve that goes from 0 to 1.3 gallons per minute. Capability. I want .5 gallon per minute flow. If it's proportional, how do I set the valve? A good example is the hand valve. How would you set that? Well, if 0 is 0% opening, 1.3 gallons per minute is 100% opening. What's 0.5 gallons per minute? And of course, to save you time, I'll go into a calculator. .5 divided by 1.3 equals about 38%. So if this is a proportional system, well, how do we want to set our valve? Well, 38% valve opening. And in the system we have out in bay 1, what do we do to get that valve opening? We have a diaphragm valve. We set a flow rate to it, to the IP converter that controls it. 4 to 20 milliamps generates a 3 to 15 psi gauge signal to the diaphragm, sets it, we get an opening. So what does this affect is manipulated variable. Yeah, it does affect the control variable, the flow rate, no matter what we want to get here, whether it's flow or whether it's level. To achieve this kind of flow, the control is the flow rate, and manipulated variable is the valve opening, the signal going to the valve opening. That's how we do it in a proportional system. What if the only thing we can do is on-off? Which is simply a solenoid valve, on-off. What can we do there? Well, solenoid valve, on 38%, off 62%. Does that look like it might achieve the same thing? Sure, just on time average, yes. We get an average flow of about 0.5 gallons per minute probably. That's how we do it on-off. Now, of course, but this gives us pretty close to 0.5 instantaneously. This clearly does not. This is either 0 or it's 1.3 gallons per minute, but it's duty cycled to give us roughly the same effect as 0.5. Now, if we can tolerate the on-off capability, then all we're looking for is average flow rate. In other words, to say fill a tank. Nothing wrong with this. Works very nicely. If we have to have the flow rate set to a certain thing because we can't tolerate fluctuations, then you go proportional. So what you see between proportional and on-off, two things. One, can we tolerate fluctuations? If we can, on-off looks good. The other thing in there is reaction time. We'll get better reaction on proportional than we will on-off in general. In other words, if I want to change the 0.5 to say a 0.7, let's nudge this a little bit more open. Here, we change the duty cycle in there, but it does still have this little bit of reaction time. It's kind of minor, but in a very large system, we might notice it. But usually you get around to, if you can't live with fluctuations, this is better. If you can, this is definitely cheaper. Solenoid valves are a whole lot cheaper than diaphragm valves. So it makes sense, that works, and they're both adjustable. Quite a bit. In fact, it's pretty easy to see this adjustment. Most process control at work is going to be on-off as opposed to proportional. It was just a matter of I need to fill up this tank, I need to have so many gallons. This works fine. Even if it has to be a flow rate at a certain time, this will work fine. If it's the case of, say, donuts rolling, it's unitized. In other words, you get so many donuts in the belt and the width. So that's how many donuts you make per gloop, per glop. That can be on-off, but pretty much get the job done. The oven's on-off. We turn it on, we turn it off, let the time run, it's done. There's an awful lot of on-off control. Over time, the accumulation, and you see how the accumulation is done as a duty cycle. That makes it near proportional capability. You see that's very popular to do it that way. It doesn't just have to be we're running full bore on or off. Most of the time you're going to see it chopped. And what you look for in power, because you have to, if you measure this with a multimeter, the things you're going to measure is you're going to see on, off. Now depending on how fast it switches. On a big system, it's many seconds. So you're going to have plenty of time to see this on a meter. If it's a very small system like fit on this tabletop, it can be switching in less than a second, in which case your multimeter is not going to be able to keep up with it. The sampling, because they sample on there. Many of you have been in the lab and you've seen numbers flicker on voltage measurements. That's due to sampling rate. The faster it samples, the less flickering you would see. But you're going to see some flicker. And if you can live with that, that's fine. On off, you can see a lot of flicker. If it's fastly changing. If it's not fastly changing, but say changes every 10 seconds, you'll see zero flow rate, and maybe 10 seconds you'll see a little flurry of activity, and then for another 6 seconds or so you'll see the full rate, and then you see one or two readings of flickering, and then follow through. And that's what you see on a multimeter. On the on-off clacking. If it goes up for a couple seconds, you may hear the relays kicking back and forth too. You won't hear it in the proportional because it's very slow moving, but relay clicking, which is on-off almost always, that you would hear. So it's a little advantage in on-off too, as far as hearing things. Any questions? It's a good stopping point, so I'm going to stop here and I'll continue on with the on-off control Wednesday.